Hello and welcome to the Unit 7 Section 3 video on writing and solving exponential functions. So this section is going to wrap up the unit here, and we're going to talk a little bit about growth and decay functions and compound interest and just how we can use exponential functions to model things. So we're going to start off with growth and decay functions. Recall that exponential functions increase by a common ratio. We learned that in the last section. We say that they increase exponentially. Exponential functions can model exponential growth or decay. We can use the function f of x equals a times b to the x to write equations that model these examples of exponential growth or decay. Now remember that a in front is just typically your stretch or your compression. It's that leading coefficient that every function has. A is still a. It's the same a that we've always dealt with. Remember, b is your base for your exponential function, because remember your x is up in the power. In the equation, a, which is your coefficient, represents the initial amount. B is equal to 1 plus the rate of change. So in the cases of exponential growth, the variable b is greater than 1. In cases of exponential decay, b is going to be less than 1. Remember, it can't be 1, because if it's 1, nothing's changing. Okay, so b has to either be greater than 1 or less than 1. And it also cannot be 0. Using the definition of rate of change, we can write the exponential growth and decay function in terms of the common ratio. So basically we're taking 1 plus the rate of change and we're putting that in for b. And remember, a is your initial amount, r is the rate of change. So the rate of change can be calculated by determining the difference between the two terms and dividing by the first term. So your rate of change is your new number minus your old number divided by your old number. Okay? You're going to see some examples of how that works here as we do example 1. So let's take the following table that models exponential growth of the money in a bond fund. So we start off with $1,500 and it grows from there with each passing year. So the starting amount of money in the fund is $1,500. And the ratio that the amount the fund is increasing by, well, we find that, again, by using this formula that you're given up here. So we are going to take our new number, in this case would be $1,593. You're going to subtract your old number, which is $1,500, and you're going to divide it by the old number, again, being $1,500. So when you do that, you're going to end up with a decimal, and the decimal you end up with is 0.062, which is also 6.2%. Now in the equation, we are not going to use the percent form. We're going to use the decimal form. It's important to note that. We're going to write the equation right here. So remember, the form is y equals a times 1 plus r to the x. Okay? So what is our initial value? It's 1,500. That's our a. Then we have 1 plus our rate of change, which is 0.062 to the x. We can simplify how this is written a little bit by adding what's in the parentheses. And that's just simply 1.062 to the x. So now that we have a formula, we created this formula specifically for this situation. So now we can use the formula we created to find out some stuff. So how much money would be in the account at the end of 10 years? So we just take the formula we just made, y equals 1,500 times 1.062 to the x, and our x value is going to be 10 in this case. And so when you put that in, since we're dealing with money, you're going to round it to the nearest cent. So we get 27.3739. Oops. 27.3739. If we want to find out how much money will be in the account at the end of 20 years, you're going to do the same thing. You take your formula that we created, and we're going to put it to the 20th power. And in this case, we find out that we get 49.95 and 53 cents. And you can really put in any time frame. If you want to find out how much would be in the account after 100 years, you could find that out by using that formula. So I don't think there's anything particularly hard here. It's just about knowing where to put the pieces to the puzzle. Let's do another example. This time we're dealing with exponential decay of a fish population of Lake Placid. Okay, so what's the beginning population? It's 14,204. What is the ratio that the population of fish is decreasing by? Well, to find that out, we take the new value, which here would be 134.94, subtract the old value, which is 14,204, and divide it by the old value, which is, again, 14,204. And when you do this, you're going to end up with negative 0.05, or a decrease of 5%. So let's write an equation that represents the exponential decay. We have y equals, just to give you a reminder of what the form is, a times 1 plus r to the x. A here is our initial value, which is 14,204. R is going to be negative 0.05, and then we have to the x. And we can simplify this down a little bit, again, in the parentheses. 1 minus 0.05, that's going to give us 0.95. So now that we have an equation that we've created to model the situation, we can find out a few things. So what is the fish population at the end of 10 years? Well, we're going to take our model and we are going to put in for x 10, just like we did before. And we would expect the number to be lower than our initial because we are dealing with decay, and indeed it is. 8504 is the population at the end of 10 years. How about after 20 years? Well, you put into your equation your exponent's 20 this time, and you have 5091. Now, it's important to note that when dealing with population, you always want to round down, since you cannot have a fraction of a person or an animal. You cannot have a fraction of a living being, okay? So always round down to account for that. Now that we have a basic understanding of modeling using an exponential function, let's take it up just a notch and talk about compound interest. So compound interest is a pretty regular occurrence in the world of banking. And compound interest is interest added to the principal of a deposit. So the principal is your initial value. It's whatever you initially put into your savings account. It's whatever you initially borrow in a loan. That is the principal. Compound interest is the fact that when interest is added, then the next time they do an run interest on the account, the interest from the previous run is also going to be counted in on the interest in the new run. So it's very easy to see how interest can add up very, very quickly, especially if you're at a high interest rate, which is good if you're working with a savings account. It's not so good if you're working with a loan or credit card debt. So the formula for compound interest is given here, and you can already kind of see the same structure here. We've got our initial value on the front, that's our principal. We've got 1 plus something, 1 plus our rate of change, but our rate of change has to be divided because we have an annual interest rate, which is given here in this R. We have to divide it by the number of times that the interest is compounded per year. And that's also part of the exponent. And then t is the time in years. So t is what we were using before for x. It's how many years down the road, how much are we going to have in the account. To help you out with n, the number of times that it's compounded per year, let's take a look at what the value for n is for different types of wording. So if n is the number of times it's compounded per year and it's compounded yearly, our value of n is going to be 1. If it's done semi-annually, which means twice a year, then it's going to be 2. Quarterly, your value for n is going to be 4. Monthly, it will be 12. Weekly, there's 52 weeks in a year, so it would be 52. And daily, 365 days in a year. Typically, of course, there is leap year every 4 years. All right, let's take a look at an example of how this works. Formula is already provided here for you, so we're just going to plug in things as we see them. So Harry invested $5,000, so that is our principal, $5,000. And then we have 1 plus, at a 5% interest rate, so our interest rate is 0.05. Remember, you have to put in decimal form. And it's compounded quarterly, so quarterly is our n, so that's going to be 4, and 4 goes up here. How much will the investment be worth after 5 years? That's our t, 5 years. So you put all that into your calculator, and you're going to get 64, 10, 19. Remember, when dealing with money, go to the nearest cent. Graham's grandparents started a savings account for him when he was born. They invested $100, that's our principal, in an account that pays 8% interest. So that's our R in decimal form, compounded annually, which means n is 1. How much is the account on his 16th birthday? So 16 years later, that's our T. You put that into your calculator and you find that the account is worth $342.59. Now, there are some situations where it is helpful to calculate the amount of money that needs to be deposited into a savings account to accrue a certain amount of money over time. This is important in case you know you have a certain type of savings account that is going to grow this certain amount of money due to interest. Say you're trying to save up to do a project at home or something, and you need to know how much you need to deposit to get enough money 3 years down the road to pay for that project. Well, here's an example of that. Granite countertops for a small kitchen were quoted at $4,200. How much should we put into a bank account right now in order to have $4,200 saved in 3 years if the interest rate is 6% compounded daily? So here's our equation. We know that we want to get $4,200. And we need to figure out how much to put in. So that's our P. That's what we're going to solve for. Our interest rate is going to be 0.06, and our N, if we're compounded daily, is 365. And that's going to go up here as well. And we know we want to get that amount in 3 years, so that's your T. Well, what you're going to do is you're going to take all of this, that the P is being multiplied, you're going to divide each side by it. So you're going to divide it from 4,200. Now, don't put this in the calculator and get a decimal and then multiply that by 4,200 because you're going to get a rounding error. So you need to put 4,200 on one side, divide it by everything here just as it is. Now, since it does come out to a whole number, if you want to go ahead and multiply this 3 times 365 and get 1095, that's perfectly fine. But this is going to give you P. Put all of this in the calculator in one go. And when you do that, you're going to end up with 3508, so $3,508.19. That's how much you need to deposit to have $4,200 3 years down the road. All right, let's do another example of this. How much should be invested to have $20,000 in 5 years if the interest rate is 12% compounded monthly? And we're going to round this to the nearest dollar. So here we have A. A is 20,000. That's what we're aiming for. We need to know how much to put in, so that's our P. Our interest rate is 12%, so 0.12. And we're compounded monthly, so that's 12. 12 up here as well. And we want to have that in 5 years, so that's our T. Well, this one we can actually simplify pretty nicely without having any rounding errors. So we have 20,000, and we're going to divide that by this. So let's simplify the inside. If you do 1 plus 0.12 over 12, well, 0.12 over 12 is going to give you 0.01 when you divide this out. 1 plus 0.01 is 1.01. And then 12 times 5 is our exponent. That's 60. That's a little bit simpler to put in the calculator. And when you do that, you're going to get $11,009. So that's how much you need to deposit to have $20,000 5 years down the road at that interest rate compounded monthly. All right, we're going to wrap up this section and this unit with writing exponential functions, okay? So let's write some exponential functions to basically bridge us into doing a little bit of solving, okay? So recall the form of an exponential function. F of x equals ab to the x, where a is the coefficient giving compression or stretch and b is the base. A is also known as our initial value in some of those cases. Generally, b has to be greater than 0 and b cannot be 1. When provided with 2 points, simply write 2 equations using each set of coordinates for x and y. Then solve the system of equations for a and b. So let's do an example of this. We're going to write an equation for the exponential function passing through the points 2, 3, and 4, 27. So if we have 4, 3, and if we have 2, 3, we're going to write that one as 3, that's our y, equals ab to the second, because that's our x value, just like it is up here. F of x is our y. We're going to do that for the other one as well. 27 equals ab to the fourth. Now, let's solve this system of equations. Well, it's not as far-fetched to solve as you would think. Let's divide each equation by each other. So we've got 27 on this side equals ab to the fourth. On the other side, from the other equation, we're going to divide by 3 and ab squared. Well, 27 divided by 3 is 9. The a's cancel, and then you have b to the fourth divided by b squared, which gives you b squared. And then 3 equals b. Now, you may be asking, well, what about plus or minus on this, because we took the square root of each side? In this case, we're not going to worry about the plus or minus, and there are reasons for that, but I'm not going to get into them here. So for now, square root of 9, we're just going to say 3. Now let's plug in b equals 3 into one of the 2 equations to solve for a. So let's do it into the first one, because that's the easier one to do. So we've got 3 equals a times 3 squared. 3 equals 9a. And so you have 3/9, which is 1/3 equals a. So what you end up with is the equation is f of x. So we'll write the equation here. F of x equals a is our 1/3. 1/3, 3, which is our b value, to the x. And so that would be your final answer for what the equation is. So we can take 2 points and write the equation for your function based on that information. All right. One final topic that we're going to cover briefly here is solving exponential equations. An exponential equation is an equation containing one or more expressions that have a variable as an exponent. One method for solving such equations is rewriting them so that the bases are all the same. This is called finding a common base. So, for example, if b to the x equals b to the y, then x equals y, provided b is not 0 or 1. So let's do this example. 8 to the x equals 2 to the x plus 6. We're going to solve this equation for x. We're going to do that by rewriting 8 as a power of 2. And we know what that is. 8 is simply 2 cubed. So we can rewrite it as 2 cubed to the x equals 2 to the x plus 6. Well, we know our exponent rules. If you have power to a power, then you just multiply the powers. So you have 2 to the 3x equals 2 to the x plus 6. Well, since our bases are the same, now we can just eliminate our bases and set our exponents equal to one another. And then from here, we're just simply solving. Subtract x from each side, divide by 2, and you get x equals 3. So that's really all there is to solving exponential equations. At least when you can get a common base, find that common base, and then equate the exponents to solve for x. All right, that does it for not only this section, but also Unit 7 as a whole. As we move into Unit 8 is the final unit of this course. We're going to be bringing a lot of what we've done together and be working with multiple function types all together as well. So all that's coming up in the final unit, that being Unit 8.